In the second part on videos of enhanced sampling methods, I'd like to build on the ideas that we have discussed in part 1, where we have looked at how we can compute free energies from MD trajectories by sampling the phase space of an atomistic system. In particular, I will start by demonstrating the application of the relationship between free energy surfaces, trajectories, and probability densities that we have introduced in the previous video. We will show that, although straightforward, these ideas actually break down when interesting configurations of an atomistic system are separated by high free energy barriers that prevent state-to-state transitions to be sampled efficiently. We will then discuss how to introduce a bias potential as a practical way of achieving a sufficient sampling of the high energy, low probability configurations that are associated with such transitions. And finally, we will look into how we can actually take into account the presence of such bias in order to come back and obtain unbiased estimates of the probability densities and of the free energies along collective variables that can then tell us something about the physics of the transitions that we have sampled in these trajectories. So, all the examples that I will illustrate in the following have been generated using Plumed, and using Plumed as a standalone solver for a simple Langevin monodimensional Langevin dynamics. And in particular, we are using these input files here, Plume.dat files and an input file that are used from the command line using the command here. So if you wish so, you can try and reproduce some of the results and of the analysis that we'll discuss in these and the following sections using similar setups for Plumed. I will just describe it briefly. So this preamble part is used to define a monodimensional space with this fictitious variable p, which is defined as a distance between atoms, but plays the role of our monodimensional collective variable space. This function defines the potential associated to this monodimensional variable space, and this command here tells us to apply that potential to define the dynamics in this monodimensional space. Then what we are doing is also collecting a histogram of the position along this collective variable space and printing it to file. So let us start by applying this approach to investigate and analyze a free energy surface that is characterized, a model free energy surface that is characterized by two metastable states, denoted by two local minima that are separated by a small free energy barrier. It is worth highlighting that in real applications, the analogous of the blue free energy surface that I'm showing here on the left is not given, and it's actually the aim of the simulation to estimate it. But in order to try and understand the application of the ideas that we've introduced in the previous video, I will start with an analytical free energy surface. So the sampling of the configuration space of this model, which is monodimensional and represented by the value of the variable s, which in real application will be a function of the atomistic coordinates of the system r, it's actually obtained by propagating the Langevin dynamics for this system. And this process will actually generate a trajectory that spans the configuration space in time. So as you can see, this is a representation of the trajectory of the system, where every point is a realization of the variable s as a function of time. So the system starts and move along the s coordinate and can move freely along the s coordinate as time progresses. So the sampling of the configuration space can then be used using the relationship that we introduced last time to compute a probability density by building a histogram. So building a histogram using the command that we have introduced here in this input file actually allow us to estimate the probability density, and from the probability density we can get a free energy surface by introducing the relationship between a probability and the thermodynamic potential that we have also discussed last time, and that I will recall in a moment. So if we do that, we get an estimate given the sampling obtained by propagating the Langevin dynamics for this system of this free energy surface, which is noisy because the sampling that we have carried out is finite and it's not perfectly converged, but it's a faithful representation of the underlying analytical free energy surface. Moreover, we can, in order to apply all the relationship that we have introduced last time, we can proceed and compute the free energy difference between the two metastable states that correspond to the two local minima represented by these potential energy, by this free energy function. So if we do that, in order to do that, actually we need to integrate the probability densities for states that belong to either one of the two basins. So we can define a dividing surface between these two states as the value 0 in this reaction coordinate, and then by integrating all the values of the probability for all the values of the reaction coordinate that are negative, and integrating the same probability density for all the positive values, we can actually estimate the probability of the two different states, and we can compute the difference in free energy between these two states. If we sample how the difference in free energy between these two states changes over time, we see that the system is actually converging to the correct answer, which is 0 for this model. And we see that this convergence gets better and better with time, and that is essentially another manifestation of the ergodic principle, which is telling us that the time averages of these, the time averages that are sampled through dynamics are actually converging to the ensemble average. And in this case, the time averages that are converging to their steady state equilibrium value are the population of the bins of the histogram that we are using to actually compute the probability density, and then integrate out to compute the free energy difference. So I just want to recall the expressions that we've used for performing this, and that are coming and that have been discussed in the previous video. So the first expression that we used is the definition of a free energy surface as a function of the probability density. So we have defined f of s, free energy surface function of the low dimensional order parameter s, is equal to minus kbt logarithm of p of s. And practically this means that we can estimate this as a histogram, and we can forget about the normalization of the histogram by essentially introducing an arbitrary constant that is not a function of s and that is rigidly shifting the free energy surface. So f of s in practice will be computed as minus kt logarithm of some So in order to recap the expressions that we used to analyze the trajectory and reach this point, I'd like to recall the few relationships that we introduced in the previous video and that were applied here. So the first important relationship relates the probability density S and the free energy surface f of s. So we compute the free energy surface f of s as minus kbt logarithm of the probability density S. And then it's useful to introduce an arbitrary constant C in order to avoid normalization problems in the normalization issues in the probability density P of S, which is practically estimated with a histogram from our simulations. So once we have the free energy surface, so let me sketch a bit the model here. We'll have that the free energy surface F of S looks like this, and instead the probability density P of S will be localized in these two states, like this. Now the sampling allows us to reconstruct this and estimate this probability density. We can then invert this probability density using this expression. And in order to compute a free energy difference between the two states, let's call the two metastable basins A and B. And as I mentioned earlier, let's consider a dividing surface between these two basins that is passing through 0 in the S coordinate. So basically we can obtain a difference in free energy between state A and state B by computing the integral of the probability density for the states that belong to A and belong to B. So basically we compute delta F AB as minus KT KBT logarithm of the ratio of the probability of A divided by the probability of B, where the probability of either A or B is given by the integral over the domain, let's call it S, that belongs to state I, of the probability density P of S in the S. Now, this amounts in practice to computing all the instances in which the system is visiting a configuration in S that belongs to state B and to state A. So essentially, once we analyze our trajectory, we can count the number of times we visit a configuration that belongs to A or belongs to B, so that is either negative or positive, and then by taking minus KBT logarithm of the ratio of these occurrences, we have an estimate of the difference in free energy between the two states A and B. This difference in free energy between the two states A and B, following the ergodic principle, will converge to the correct answer in the long time limit. So, going back to our model system, the question is this process, is this relatively simple system of ideas, is it applicable to any possible transition? So let us examine what happens when we increase the height of the free energy barrier that is separating the two metastable states, while keeping constant the computational time at our disposal. So this was the system that we just analyzed, and the barrier was extremely low, and we sampled for 1,000 time steps. So let's see what happens if we increase the barrier between the two states, keeping the sampling time constant. So if we move to a free energy surface that looks like this and that has a free energy barrier that is significantly larger, the sampling obtained by propagating the Langevin dynamic for the same type of model, for an analogous type of model, actually leads to a much more infrequent transitions between states, between the two metastable states. So as you can see, essentially, as the number of transitions decreases, Now, the question is this approach applicable to any transition? So what happens if we examine... Now the question is, this approach applicable to any transition? Let us examine what happens when we increase the height of the free energy barrier that is separating the two metastable states, while keeping constant the computational resources at our disposal to estimate the free energy surface. So in other words, by keeping constant the length of the trajectory that is sampling S through Langevin dynamics. So as you can see, increasing the barrier, so this was a reference case. If we increase the barrier, actually we obtain a much lower number of transitions between states within the same simulation time. Nevertheless, the sampling of the transitions between the two metastable states is quite frequent, and actually if we go through the process of computing an estimate of the probability density in S and computing the free energy out of that estimate, we still get a reasonable, albeit not perfect, estimate of the free energy surface. However, if we increase the barrier further, so if we keep going on with the barrier that's separating the two metastable states, we will actually reach a limit in which the characteristic time associated to a transition between metastable states is of the order of magnitude of our simulation time. So, for example, in this case, when our barrier reaches a significantly larger value, we can only observe a single very brief transition between the two metastable states. So in these conditions, it is not possible to converge an estimate of the free energy surface within the simulation time that's allocated, so without changing the constraint of the computational resources at our disposal. And actually, the answer that we obtain will be dependent on the initial conditions of the system. So if we initialize, for example, in the left metastable basin, we will have something that looks like this. Instead, if we initialize in a different metastable basin, in this case in the positive one, we'll likely have an answer that will be the opposite one, within the same characteristic simulation time. So a way to resolve this problem would be to extend the simulation. If we extend the simulation to a simulation time that is significantly larger than the characteristic time associated to a transition between metastable states, we will still be able to recover a convergent estimate of the probability density in S, and therefore we'll still be able to reproduce and reconstruct the free energy surface of our system. However, given a finite amount of computational resources, it will always be possible to identify transitions that have a characteristic time that exceeds the limits of the sampling that is practically achievable. So this is where enhanced sampling methods come in to essentially to tackle this problem with a different perspective. And enhanced sampling methods introduce algorithms that allow to overcome these sampling limitations by essentially obtaining a better sampling of the configuration space given the computational resources available. So the first, the set of enhanced sampling methods that we will discuss in these series of videos is based on the introduction of a bias potential. It's not the only possibility, but it's a subset of this type of methods. And in order to introduce these methods, I would like to discuss a bit what is a desirable probability densities that is sampled in our simulations, and how can we actually design a bias potential that helps us achieving a desirable sample probability density. In order to discuss why a bias potential might be beneficial and what could be the aim of introducing a bias potential, let's just start by sketching the usual model free energy surface with two wells. So this is the collective variable S, This will be our f of s, and our f of s will have the usual double well form. And so in such a system, as we have already sketched previously, the probability density will be localized in the two basins. And the rare transition between the two metastable states that is associated with this high free energy barrier is inherently associated with the sampling configurations that are extremely low in probability here in this region. So the probability density P of S, if we just invert the expression that we used earlier, is proportional to the exponential of minus beta f of s. And in this case, a double well f of s gives us a very peaked probability density. So that if we start, for example, in this metastable state here, we begin our simulation in this state, we will sample configurations that are close to the minimum, but fluctuations that bring us on top of the barrier and across this bottleneck essentially are very, very rare. So what is an alternative to this free energy, to this probability distribution? In other words, what is an advantageous probability density that we might want to be able to sample in a simulation in order to achieve the most effective sampling of the coordinate space projected on this variable s? Well, an initial guess could be that we may be interested in sampling a constant probability density. So a probability density that does not depend on s. So essentially, imagine we can sample every configuration, irrespective to its free energy, with a constant probability. That probability density will look flat, like this red curve. And that probability density is an example of a desirable probability density that we may want to achieve by introducing a bias potential in our system. It's actually, by some metric, we could consider it as the most efficient one, because it will allow us to sample every configuration irrespective of its free energy. So in order to do that, actually, if we go back to this expression, we have that this probability density, which is, imagine now that the red one, the red probability density, let's use the same color. The bias probability density will be proportional to e to the minus beta f of s plus some bias potential v that it's introduced into the system. So if we're interested in getting a constant probability density here, so essentially we can easily show that what we really want is to introduce a bias potential that is equal and opposite to the free energy surface. So this is basically turning the problem on its head, because we don't really know what the free energy surface is. But essentially it allows us to show that if we introduce a bias potential that counteracts the effect of the thermodynamic potential, actually we can achieve an effective sampling in a simulation. So the question then, which is a question of implementation, is how do we actually construct this bias potential so that it estimates and allow us to sample this collective variable space without knowing the underlying free energy surface. But for now, let's consider this. When we introduce a bias potential, the histogram that we will collect from the dynamic simulation is not the histogram of the unbiased probability density, so it's not the histogram of P of S, but it's the histogram that is approximating PB of S. So the probability density in collective variable space given a certain bias potential V of S. So the question now becomes, how do we actually use statistical mechanics to go from a biased probability density, so to account for the effect of the bias and reconstruct the unbiased probability density from the sampled probability density. Again, if we introduce a bias potential, what we will sample in our simulation is this bias probability density that will depend on the bias potential. And the question that we want to answer now is how do we account for the presence of such bias potential in order to extract the unbiased probability density that will allow us to recover the free energy of the system. So in order to account for the effect of the bias introduced in our system, we need to be able to compute what is the effect of the bias on the free energy. So what is the difference in free energy between a system with a bias and a system without a bias. So in order to do that, it's useful to introduce a framework in which the bias can be considered as a perturbation. So to keep things general, we can introduce now a system A, which is a reference system, and a system B, which is a perturbed system. System A will be characterized by potential energy UA of R, function of the coordinates, and system B will be analogously characterized by a potential energy UB, function of the coordinates. The perturbation delta U B A will be equal to the difference between the two potential energies of our systems. So in other words, we can write the potential energy of the perturbed system as the potential energy of a reference system UA plus the perturbation. So if this is the case, let us write the partition functions better, the configurational integrals, since we are only looking at perturbations and potential perturbations that have to do with the coordinate space. So let's look at the configurational integrals for states A and state B. So for state A, we can write ZA is equal to the integral of e to the minus beta u a of r in the r. And analogously, for B, we can write e to the minus beta ub r in the r. But now, we can actually introduce this expression for ub here. So this configurational integral becomes e to the minus beta ua e to the minus beta delta u b a So now we can multiply and divide this quantity by the partition function of the reference system. So we multiply it by z, we also divide by z. And we can now recognize that this group here is the probability density in configuration space for the reference system. So let's indicate this probability density in configuration space with PAR. Forgot the differential here. And this expression leads us to the main result of this perturbation framework, which is that the configurational integral for the perturbed system, ZB, is equal to ZA that multiplies PAR times E to the minus beta perturbation in the R. So we can recognize now that this integral is an ensemble average. It's the ensemble average of the exponential of the perturbation in the system, in the unperturbed system. So basically we have written the configurational integral for the perturbed system ZB and the configurational integral for the reference system ZA that multiplies the ensemble average of the exponential of the perturbation, delta U BA R multiplied by beta in the unperturbed system. This is useful because we can now write configurational integrals and partition functions for the reference system and perturbed system also when these two reference and perturbed systems refer to our case of unbiased and biased systems. Let us consider the reference system as the unbiased system. So the unbiased system as the reference system. So our reference will be characterized by potential energy U0 of R. And the perturbation in our system will be defined by the bias potential V, which is function of the coordinates through the collective variable S. So the total potential energy of the perturbed system will be given by UB equal to U0 plus V of S. Now, the notable result that we obtained earlier allows us to write the partition function of the perturbed ensemble, so the partition function in the presence of a perturbation V, as ZB equals Z0 multiplies the ensemble average of E to the minus beta perturbation. So this is now useful because ZB enters the formal definition of the bias probability density that we are actually sampling in simulations. So we can use this expression to write an equation for the bias probability density sampled in simulations that are performed under the effect of the bias potential V of S. So if we just do that, we should write that the bias probability density, indicated with PB of S, is equal to 1 over ZB that multiplies delta S beta U0 that multiplies E to the minus beta V of S. So now, if we take this expression that we just obtained from perturbation theory, and we use it we use it here, we can actually rewrite this equation like this. Let me do it here, so I can rewrite this. And now we can see that this part, actually these factors, define the unbiased probability density. So by integrating delta S e to the minus beta u0 divided by z0 in the R, we obtained the unbiased probability density in S. So if we carry out this expression, we get that the bias probability density is equal to the unbiased probability density that multiplies e to the minus beta v that multiplies this constant, which is the ensemble average of the bias potential estimated in the unbiased ensemble. Or in other words, if we use the perturbation formalism, this is the free energy difference that is due to the introduction of the bias potential, and that is not dependent on S. So this is a constant that is independent of S. So basically, with this expression, we have now a recipe that allows us to compute the unbiased probability density from the bias probability density and the bias. So here we have the bias probability density that is sampled, the bias that is known because it's set by us, and modular constant, which is this ensemble average, which we will discuss more in detail later on. We can actually estimate the unbiased probability density. Now this constant again does not enter this estimate because again it's constant, it's not a function of S, and the dependence on S disappears when performing this integral. So if we go back to the case that was not sufficiently sampled with an unbiased simulation, we can see that this was the case. So we were not really able to reconstruct a free energy surface with these with simulations of 1,000 steps for this particular case. Let's see what happens if we introduce a bias potential and we apply this relationship between the biased and the unbiased probability densities in S that were derived starting from perturbation theory. So in order to introduce a bias, basically, as I mentioned earlier, we want to obtain a smoother probability density, and to obtain a smoother probability density, we can aim at essentially introducing a bias that smoothens out the barrier. So in this representation, the green line is the bias potential that is added to this free energy surface, and the light blue line is the effective free energy, so the sum of the free energy surface plus the bias potential over which the bias simulation actually evolves. So if we solve a system for a bias dynamics in the presence of this bias potential, we get a very thorough sampling of the configuration space that spans from -1 to 1. So you can clearly see that if we compare this sampling obtained in the without any bias potential with the sampling obtained in the presence of the potential, we can see that all the configurations are sampled very effectively within the same computational time. Now, if we take this sampling obtained from the bias simulation and then we estimate a bias probability density using the samples obtained from this trajectory, we get something that inverted actually captures the bias free energy surface. So actually it captures the effective free energy surface over which the system is evolving. So the sum of the real free energy surface and the bias potential in the collective variable space S. However, when we apply the relationship that we have just introduced, so if we consider the bias as a perturbation, we can actually back calculate the free energy surface, and as you can see, essentially within the same simulation time, we can converge an estimate of the free energy surface to a very good degree of accuracy. So it was key in this case to introduce a single bias potential that was able to smoothen out the free energy surface. And the sticking point for this type of application is that in real systems we are not really aware of what is the shape of these free energy surfaces that we are sampling, and so we cannot really define a priori what the shape of the free energy, what the shape of the bias potential should be, what the functional form of the bias potential should be to achieve an efficient sampling of configuration space. So in order to circumvent this problem, there were different bias sampling methods that emerged in the literature. Some of them can be summarized under the umbrella of umbrella sampling, and other instead relate to adaptive sampling, and one of them, for example, is metadynamics. So in the next video I will cover those methods, and just to summarize the content of this video, we have looked at the sampling problem by analyzing what happens on simple Langevin dynamics model systems evolving on double well potential energy surfaces. And then we have seen that we can actually introduce a bias potential to improve the sampling of the configurations. And once we have introduced such bias potential, by referring to a perturbation framework, we can actually take into account the effect of the bias and recover the unbiased probability distribution that is the physical property that we are interested in obtaining from a system. So next time we will look at specific algorithms that allow us to approximate a good functional form of the bias that allows us to efficiently sample free energy surfaces without knowing a priori what is the height of the barrier or where local minima actually are in collective variable space.